All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. Let us jump into it. Okay, that looks good. What else? Yes. All right, so this was the lecture last time. Let's just first maybe talk about some announcements. So, as you guys are aware or should be aware, it's been in the syllabus for a while. Our second test is this week. It's coming Thursday, and I'm going to do it the same format as test one. And so it will be live Thursday at 3, and you have until the following day at 9 to do the exam. I also posted a practice test for test 2. It should have come live at the beginning of class, so it was up since like around 6. It is also timed, and it will be due just before the second test begins, but hopefully you do it a lot quicker than that, so you can actually look over things and learn what you need to do. So we have that. We also have that change in the homework due date. So before, homework was due tomorrow, but we're not going to finish everything for that homework, for all the homeworks. And so I extended that until, I did this a couple days ago, so I don't remember exactly when I extended it till, but I think it's also a Friday, but I might even push that to Saturday. I don't think there's gonna make a difference, too much of a difference there. Yeah, so those are the main things. So test 2 is on Thursday. Similar format to test 1, except new material, obviously. So it's going to be around 20 problems. You have to share your work for around 11 of them. There are 5, 6, 7 bonus problems. I don't remember exactly how much. I wrote it a while ago. And yeah, there's a practice test up. So not a bunch, because last time I put up a bunch of practice tests, people didn't have time to do them anyway. So just put up one. And it's a little bit longer than the actual test. I think they're like 24, 25 problems on the practice test. But yeah, that should touch on the things that you need to touch on. Now, the plan is to finish everything needed for the test today. So we should really jump right into it and try to get that covered. And hopefully it doesn't spill into tomorrow. If it does, it shouldn't be much into tomorrow's class. Hopefully we can get everything done today. And there's actually a small chance that we might get things done early. I don't know. But if we do, I'll just end the class and we don't have to go all the way till 9. So that's that. So unless there are any other questions, we'll just jump right into it. Yeah, so how the practice test works is the answers come live after the window closes. So you won't see the answers until everyone actually did it. So if you, however, so my thing is this, the test should be the case that after doing the test, you'll still be able to view the problems. You should be able to check your answers and know whether you're right or wrong. If you finish before the test, the window closes for the practice test, and on top of that, you can't figure out your answers on your own, which is, you probably should try to do that because it will help you prepare for the real test. Then you could just ask me, hey, on the practice test, I couldn't figure out the answer to this. Even after I looked at it for an hour afterwards, I didn't figure it out. Then, I can individually just kind of answer questions there. But it's kind of set up so that the answers aren't presented until the window closes. So yeah, so that's there. Any other questions, concerns before we jump into things? All right. So with that, let's actually look at what we did last time. We learned about things called parametric curves, which was essentially us taking something, well, the dimensions can go all over the place. But for us, everything is in like 2 dimensions. We're taking something in the XY plane and we're treating the X coordinate and the Y coordinate as some separate entities where we can track them individually by their own functions. And that has a lot of benefits to it. So we learned about what parametric curves are. So the X coordinate is being tracked by its own function, the Y coordinate is being tracked by its other function, and it's traversed as the variable there defined in terms of, someone's trying to get in here, is which is called the parameter. So you have a parameter and your X and Y does something based on that parameter. And when you look at the X and Y as a coordinate, it traces out a curve in the plane. And doesn't have to be 2 dimensions, can be higher dimensions, but that's basically how we form a parametric curve. It's like you're using a function to measure each individual component. And we looked at how to sketch a parametric curve, but we also looked at the fact that there are some standard ways to construct curves. And we looked at standard ways to construct circles using parametric equations. And by the way, when you actually write down a set of parametric equations for a curve, you say you've parametrized the curve, or you found a parametrization of the curve. And so it's just a different way to talk about the curve. So instead of talking about, y as a function of X, and you have X depends on Y, you can have X depend on another variable, Y depends on that variable. This variable is called the parameter, and you can get that. This idea is going to be extended when you go into Calc 3. So the number of parameters really talk about the dimensions of the object that you're looking at. So when things depend on 1 parameter, you get a curve. If they depend on 2 parameters, you get a surface. They depend on 3 parameters, you get a solid object, right? They depend on 4 parameters, you get a 4-dimensional object, and so on and so forth. So for us, we're going to stick with like 1 parameter. So things are going to give us curves. And we know how to get a circle. We know how to get various parts of the circle. We looked at how to parametrize straight line segments. And we looked at how to parametrize almost anything else. There are some more tricks to be had here, but this will cover everything else you'll need to do in Calc 2, and most of everything else you'll need to do in Calc 3 and above. And we started looking at calculus with parametric curves. So once we actually write things in this new way, how do we do calculus? How do we find the derivative? How do we find the slope of the curve, etc.? And we looked at equations for how to find the slope and how to find the second derivative. And we can do with those things the same sort of things that we've always been doing in Calc 1. We can find tangent lines, talk about concavity, we can talk about increasing or decreasing of the curve, etc. So we actually did some problems on that. Then we looked at arc length, and I think this is around where we wrapped up. So it's using parametric equations, we can use integrals to kind of as an application to figure out the length of some curve, which can be important in various scenarios. And we derived the formula being this. So assuming you have a smooth function, it's going to be called, meaning you can find all the derivatives, they're defined. Then you can actually find the length of a curve that's parametrized by x of t and y of t in the following way. Just assuming that it's traversed once as you move from A to B, and it doesn't do things like go back and forth, because then you'll get multiples of the length. But as long as it traverses once as t goes from A to B, then you can find the length of the curve in this way. And we actually derived that formula for that here. And then we did an example where we found the length of this blue curve by just doing an integral. So this can be thought of something with parametric equations, can also be thought of an application of integrals. Now, another thing that's covered in another chapter was how to find the length of a curve if you don't have it as a set of parametric equations. And that's where we're going to start here. And we're going to start by deriving that from this line that you see right here. So we're going to start here, and instead of going the parametric route, we are going to go another route. So let's actually do that, right? So we looked at the fact that, just some more vocabulary, that the way we've been doing things, we call it the scalar form. And so now I was basically teaching guys how to do things in the parametric form. And so there's a scalar version of your arc length formula, and that's what we're going to do. And scalar just basically means magnitude, as some of you might recall. So when you have y equals function of x, you can think of it as f is giving you the magnitude of y. It tells you where on the y-axis you want to plot that point. Parametric equations are very useful for vectors. So if you want to describe a curve in space, it's very useful to describe it as vectors, and the parametric equations will form the components of a vector. And so the parametric form is often called a vector form, and the regular thing that you're used to, y equals f of x, or f of x, y equals c, is called a scalar form. And we actually want to derive a formula for the length here. And so we're actually going to pick up partway through our other derivation. Go back to the derivation for arc length in the parametric form. Pick up at. So we got to a point where we say the length is approximately equal to the sum of the lengths of these line segments, right? So it was like I equals 0 up to n, and we were looking at things like delta x squared plus delta y squared. And that and this, remember, this was just like xi minus 1 squared. And we call that difference delta x, the change in the x value. And the delta y was the change in the y value, which was a very similar idea. So that was yi minus 1 squared. Okay, so we're picking up from that point. Now, it turns out one thing we could have done is we could have factored out a delta x squared. So you see writing infinity up here. That's equal to that. Now, delta x is always positive. So while this is the absolute value of delta x equals delta x, since delta x is positive, well, it's actually strictly positive. It doesn't make sense to actually do that. And so this would just become this guy, 1 plus delta y over delta x. Like that's kind of like your dy over dx kind of thing. And so again, this is something that we can get the exact length of the curve by looking at this as just the Riemann sum. So we take the limit as n approaches infinity of that thing. I'm writing infinity up here. And of course, your delta x becomes dx, your delta y over delta x becomes your dy dx. And so we end up with the integral from a to b of the radical of 1 plus dy dx squared. Right? That leads us to this formula. So this is the arc length of a scalar curve. So not if you have switched to parametric equations, but you have a curve that looks like y equals f of x between on the interval of a, b, and you know that the derivative can be found, it's continuous, then you can find the length of the curve with this formula. And again, it's from using a bunch of line segments and summing them up, letting the number of line segments go up to infinity, you get a Riemann sum that gives you an integral. So the parametric version of arc length is here. It's the integral of the radical of x prime of t squared plus y prime of t squared dt. When you go to the scalar version, it's actually the radical of 1 plus f prime of x squared dx. And so that's you take the integral of that. And this is actually a form you're going to see in Calc 3 again, but I won't talk about that. It's not going to give us much. So yeah, we just have this formula now that we can actually use to find the lengths of curves. And we had a bunch of examples. And so I have them written out here, and I have the answers written out, kind of because I expected to get to this point on Thursday, and then you could actually try it on your own and check your answers. But we're here now, so let's actually just do these. So here, we're going to find the exact length of this curve. So that's like your y equals f of x here. So this here is your f of x. And we have our x going from A to B. And so, yeah, you can just jump straight into the formula. So the formula is going to be something that I expect you to have like memorized. So you don't have to derive it anytime. So anytime you need to use it, you would just jump into the formula. So here we have that. I'm just going to use L for length. L is going to be the integral. Oh, let's actually find the stuff first. So here we have f of x equals ln of cosine. This, of course, means your f prime is going to be u prime over u. So it's the derivative of cosine over cosine. It's going to be minus sine x over cosine x, which we should know is minus tangent x. And so now this would mean, I can probably put that up here. This would mean that L is equal to the integral from A to B of the radical of 1 plus f prime of x squared. This would be 0 to pi over 3, because those were my x limits. And this is going to be the radical of 1 plus tangent squared x dx. Okay, so how do I do this integral? Ideas? Anyone? Ideas? Okay, so I see someone in the chat here telling me I can replace 1 plus tangent squared with secant squared, which is actually the case. So here, so that's just secant x dx. Technically, this is absolute value of secant. However, we know that secant is positive on 0 to pi over 3. How do we know that? Because the cosine is positive on 0 to pi over 3. So cosine is positive between 0 and pi over 2, and pi over 3 is in a little bit before pi over 2. So we can actually ignore the absolute values and just integrate secant. So that would be ln of secant x plus tan x between 0 and pi over 3. So that's secant pi over 3 plus tangent pi over 3 minus ln secant 0 plus tangent 0. All right, what's secant of pi over 3? Some you should almost know by heart. What you should know is cosine of pi over 3, and then you just take 1 over that.
Two.
Right, so we had that table where it went pi over 6, pi over 4, pi over 3. The sine went 1, 2, 3. The cosine went 3, 2, 1. And so 3, 2, 1, you're going to divide it by 2 and take the radical of the top. So that's a half. So at pi over 3, the cosine is a half. And so the secant is just going to be 2. Similarly, because you know that in that column, the sine is going to be radical 3 over 2. The cosine is going to be 1/2. You take radical 3 over 2, you divide it by a half, you just get radical 3. So you know that the tangent is going to be rad 3. Secant of 0 is just 1 over cosine of 0. Cosine of 0 is 1. And tangent of 0 is 0, right? So that just goes off to 0. So we just have ln of 1 here, and we know that log of 1 is also 0. So we just have this guy. This is the length of the curve, the exact length, ln of 2 plus rad 3. So it's just applying this formula to a function, and you do the integral that results. In theory, at this point, everyone's an expert with integration, although I know, can't really tell by me asking questions to the class because no one really talks to me, except some people in the chat occasionally. But I'm assuming that you get, at this point, you can get any integral and you'll figure out how to do it. That is the assumption. So yeah, let's move on to another example. So in this example, I'm just leave some of that one here. This example at the bottom of the page, find the exact length of this. Now, again, remember integrals are really, when I give you a formula, it's kind of like a dummy variable, how x is used. So this is just an example to show you, it doesn't matter who's on the left or the right. You can still do thing. So here you actually have x equals some function of y, but it doesn't, and you have like a y between a and b, but that really makes no difference if I switch the name of the x and the y, it's not going to make any difference. So here it's just a matter of just using L equals the integral from a to b of 1 plus f prime of y dy. There's nothing going to change really. So here I know my f of y is y to the 4th over 8 plus 1 over 4y squared. And so my f prime, the derivative of y to the 4th is going to be 4y cubed. The 4 is going to cancel into the 8 2 times, so it's y cubed over 2. And then plus, so remember, this is 1/4 y to the minus 2. Bring the minus 2 down, it's going to give me a negative a half. And then subtract 1 from the power, so I'm going to get y to the minus 3. So there's a y cubed in the denominator here. So we have that. And so now we can just plug this in. We're going to use L equals the integral from, well, this is right down the formula, a to b of the radical of 1 plus f prime of y squared dy. So in this case, that is going to be 1 to 2. 1 plus, here we're going to have y cubed over 2 minus 1 over 2y cubed squared dy. So now I have to figure out how to integrate this. So you'd notice that as is, none of our techniques are going to really help us here. So I'd probably expand that square, see if I can see anything. It's going to be 1 plus, square that, you get y to the 6 over 4. This times this, you get a quarter times 2. So you get minus a half. Plus you square this, 1 over 4y to the 6. I don't know if you can see that that's a 6. Now the 1 plus the minus a half, well, that's going to be a half. I'm going to write it in the middle here to be very suggestive. Anyone see how to integrate that? Any ideas? So the hint would be to compare this with this. So compare. What do you notice, if anything? Does anyone notice anything? Right, it just changed the sign. Well, in that thing squared. So we know that the top thing that I just underlined is actually this thing all squared. So there's a negative sign in the middle, so you have a negative half. So you can just realize, oh, this thing that I have on the bottom line, it's just like that's that thing, but the middle sign is positive. So it should retract or factor into the previous complete square that I had, but with a positive sign. So that is the thing to notice. So this must be actually y cubed over 2 plus 1 over 2y cubed all squared. And you can actually check that that is the case. Like if you actually square that, you would get what we have there. And so, of course, this cancels that. And again, technically you get an absolute value here, but you can ignore it because it's positive. So you have y cubed over 2 plus 1 over 2y cubed. and y is going from 1 to 2, it's always going to be a positive number, right? If you plug in y equals 1, all the values to y equals 2. A positive number cubed is positive, and so when you're taking these fractions, they're all positive. So now we just have to integrate this. So this, of course, is just a half y cubed plus a half y to the minus 3. So we can just do the power rule. So add 1 to the power, divide by the new power, plus here add 1 to the power, and divide by the new power. So it's going to become a minus. Okay, so now we have the fundamentals of the theorem of calculus to apply. And so now if I plug in 2 to the 4th is 16 divided by 8. That's 2 minus 2 to the minus 2 is actually a quarter, so that's going to be like 1/16 minus if I plug in 1, I get 1/8 minus 1/4. Right. So now I just have to do that. So I guess I can write everything over as 16. So this is 32 over 16 minus 1 over 16 minus 2 over 16 plus 4 over 16. So we get 33 over 16. Right, which was the answer, 33 over 16. Okay. So again, it's just knowing the formula. When you want to do arc lengths of something, depends on whether you have it in scalar form or parametric form. So in scalar form is just an application of this integral formula, and in parametric form, it's just an application of this integral formula. But they're actually pretty straightforward to apply. The hardest part is actually doing the integral, which now, after this class, you would know how to do that integral. Not that the integral is easy in general. There are sometimes the integral is crazy hard to actually do by hand, in which case you would approximate it, again, using methods that you would know from this class or some sort of computer algebra system. But theoretically, it's just a matter of applying this formula, finding the derivative, plugging it in, and then doing the integral. And for us, it'll always be an integral that you can actually do using the techniques that we learned in this class. So yeah, that's that. So now that sort of ends this discussion. We actually want to go to a new section where we are going to learn about a whole new coordinate system called polar coordinates. Now, this is actually related to parametric equations because it's developing a new coordinate system based on some specific parametric equations, and these parametric equations don't change. Kind of like how in trigonometry we had those parametric equations and it gave birth to the rise of trig. We're going to have similar parametric equations they're going to give birth to a whole new type of coordinate system, a whole new way of looking at points in the plane. So polar coordinates, it's the name of the elements in this coordinate system, and it is to be, I guess, contrasted with what we call the rectangular coordinate system, which is the coordinate system that we're used to using. Now, a coordinate system is just a way to like locate points in the plane and talk about where you are in the plane. And then really, when you write down the equation of a curve, it's just a location of multiple points all at once that you can actually connect with lines and make a picture. So that's what we're going to do. So just to remind you of the rectangular coordinate system, not that any of us need reminding, but kind of just to see where the name comes from. If you had to locate the point 1, 5, just in the usual XY plane, how you normally think of it, or 3, 1, or -2, 3, there is a way that we can do this. So this would be the X, this would be the Y. And so let's say you're trying to find 1, 5. the point of the rectangular coordinate system is to be able to locate this point in the plane. So what you would do is you'd go 1, and then you'd find the point 5. And what you do is you extend a horizontal line from the 5, you extend a vertical line from the 1, and that point here, where these two meet, that is the coordinate 1, 5. You'll notice that you've created a rectangle where one of its vertices is at the origin. And this is why it's called the rectangular coordinate system. So it's all based on rectangles, and one of the vertices of that rectangle is going to be the origin. And so, but that tells you how to find the point 1, 5. Where is it actually located? So that's this guy. Similarly, if I wanted to locate 3, 1, the first number just tells me the location on the x-axis. The second one tells me the location on the y-axis. And you play the same game. You extend horizontally from this, extend vertically from that, and you can get another point. This is the point 3, 1. And again, you can see that there's this rectangle that was formed. That's why it's called a rectangular coordinate system. And so we can get that point. Now, negatives, and this is actually important conceptually. So we know negative just means you essentially reflect the positive numbers, reflect over the origin, and then we put negative signs on all the other ones. So while we're going like 1, 2, 3, 4 in this direction, we go -1, -2, -3 in that direction. So you can think of negatives as a change in direction or reflecting or moving in the opposite way. So normally when I see 1, 5, I know I move 1 to the right because it's a positive, and then I move 5 up, right? So the positive direction is to the right for X and it's up for the Y. The negative directions actually go the opposite way. So if I wanted to go -1, I would go to the left, -5 would bring me down, right? And so the signs of the numbers in the system can actually indicate to you directions in which you want to move. That's going to be an important point for what we're going to talk about later, because there's going to be something where I'm going to talk about it being negative, and you're like, well, I mean, it doesn't really make sense to talk about negatives here, but negative in this context would mean a change in direction. And that is actually an idea that we even saw last time. We were talking about when we did the parametric curves, and we said if we wanted to reverse the direction, we could just put in a negative sign into one of the equations, and that would actually reverse things. But similarly here, negative would just means reversing. So when I have -2, -3, it means I move 2 units to the left from the origin. So bring me probably a little too far. And then 3 units down. And again, you play that same, and you can get another point. This would be the point -2, 3. So this is how we locate points in the plane. And of course, an equation of a function like a y = f of x is just something that tells you multiple points at the same time. So you can sort of connect them with a curve and get a picture from them, right? So that's one way to actually view the rectangular coordinate system. So about locations, and you can figure out where on a curve you are based on the system, and it's constructed by just using a bunch of rectangles. So here's the idea. There are times when that is actually very inconvenient, and you're not fully going to appreciate why that can be inconvenient now. That is something that you're going to see when you go into higher dimensions. Well, there are some cases where you can even see it in lower dimensions. So we're actually going to look at it this way, but it becomes really important to be able to think of the coordinate system and how to locate points in space in ways other than the rectangular coordinate system. And when you go to Calc 3, you're actually going to learn about 2 different coordinate systems. One is going to be based on the polar coordinate system, which we're going to look at now. So it's actually very important for you to get this concept down in 2 dimensions, so that when you go to 3 dimensions, it's not going to be that bad. And it will be called cylindrical coordinates when you get there. There's also another one called spherical coordinates, which is actually very useful in physics in particular. But it's It'll be because there are certain things that you change the coordinate system to make it easier to do calculations easier, to conceptualize things easier. And so it turns out conceptualizing things in terms of rectangles can make things pretty annoying sometimes. And so we actually want a different way to locate things in the plane. And here's how we do it. We do it based on circles. So this is just a blurb explaining, how rectangular coordinates work and the fact that we're going to find a different way to locate things in the plane. But instead, we're going to use it in terms of circles of a certain radius and angles. And it's kind of going to be very similar to how we actually set up trigonometry. But so here's how the thing. So it's like given a point. So here's a point out here, right? And we want to be able to locate that point. I don't want to put it up there. Let's put it down here. Okay, so one way is to locate with a rectangular coordinate system. How far do I have to move horizontally and vertically to get to that point? And I can address what directions I'm moving in based on negatives and positives. But here's another way. What I can do instead is I can find a circle centered at the origin where that point is on its diameter, right? So there's like a circle here, right? Find a circle centered at the origin. With the point on its perimeter. I said diameter, but technically, I guess it is a diameter. Right? So we have that. Right? That's one thing we can do. And now here's how we're going to actually locate that point. We're going to extend a line from the origin. Right? So again, we have this point. We know a circle that it lies on top of. And we're actually going to extend a line from the origin to meet that point. So there's a line going like that. The length of this line we'll call R, because it reminds us of the radius of a circle, right? Now, we can also measure the angle made with the positive x-axis, much like in trigonometry. Call that theta. Right? And so you can actually say call R the length of the radius, i.e. the distance of the point from the origin, and call theta the angle made with the positive x-axis. Right? Now it turns out you can actually describe a location with these two numbers, right? So tell me how far from the origin I'm at, and tell me what angle I'm at away from the positive x-axis, and I can actually tell you the exact location, right? So this leads to the fact that we can have this coordinate out here, and we can know how far it is from the origin, R, and then we can know what angle it makes with the positive x-axis, and we can actually use that as the identifying numbers. We can call this R comma theta. So I can actually give you a pair of numbers, and the interpretation of this is not how much we move on the x and the y, but it's rather how far am I from the origin and at what angle am I from the positive x-axis. And using those two numbers, we can actually write down a way to locate this point. Now this, when you express things in this way, not in x comma y, but rather in r comma theta, in terms of the distance from the origin and the angle you are from the positive x-axis, this is what is called polar coordinates. So this is called a polar coordinate. And yeah, so not all the time you have to like think about it as like a circle. So if I have a point in the plane, again, you can just think, what angle am I here and how far do I have to extend a line to hit that point, right? So you can actually imagine this devoid of the circle. But again, because of trigonometry, we know we can actually form right angles here and actually talk about how to measure certain distances and get certain things from that. But essentially, you just thinking of the location of a point based on its distance from the origin and an angle with the positive x-axis is what leads to the polar coordinate system. Okay, so that's it. So polar coordinates locate points in the plane based on their distance from the origin and the angle made with the positive x-axis. Okay, so that's it. Once you actually find this way of locating a point, you say you're locating it in the polar coordinate system. Okay, so that's I said everything here that I just said verbally, so I don't think you have to do anything like that. So I can talk about locating a point like r equals 1 comma pi over 4, r comma theta equals 1 comma pi over 4. So here, someone's coming in here. So here, when I see 1 comma pi over 4, I'm not thinking of it as x is 1 and y equals pi over 4. No, I'm thinking of it as r is 1 and theta is pi over 4. And basically what that means is I know exactly where to find that point, right? So I know I'm going to move at an angle of pi over 4, which I know means I'm going to be along this line at 45 degrees. And then I want to move a distance 1, right? So I'm going to move on here from the origin, extend a distance of 1 unit. This coordinate here is the coordinate 1 comma pi over 4. Any questions on that? Like how the system is set up, how we locate points or anything of that sort? Okay, now here's something that's interesting about the polar coordinate system. Addresses are no longer unique. So when I say the point 2 comma 3 in the rectangular coordinate system, there is no other way really other than just finding a different way to express 2 and 3, which is like cheating, right? So, okay, I can write 2 as 4 over 2 and 3 as 3 over 1 or whatever, and it looks different, but it's the same thing. But no, when I put 2 comma 3, and those magnitudes are what matter, there is no other point. If I change the 2 or I change the 3, I change the location, the address changes. It turns out with polar coordinates, you can actually change the numbers in your system and the address can stay the same. And that's because we're using angles. So one thing you can notice is that this is the same as if I were to ask you, oh, locate the point r theta is 1, 9 pi over 4. So I can literally change the value of the second coordinate. And you know what? The address is not going to change. Because I can just go around. This is 8 pi over 4, and then I go 1 more pi over 4. And then I extend from that point a distance of 1. And I would actually get the same point, right? So me writing 1, 9 pi over 4, it's equivalent to someone giving me the address 1, pi over 4. They'll actually give me the same location. And as you can probably imagine, I could kind of redo this. I can keep spinning around. And here's where negatives come in as a change of direction. I could measure the angle as negative, and that just means I go clockwise instead of measuring the angle counterclockwise, right? And so, in other words, polar coordinate locations are not unique. Okay, so there's an infinite number of ways that I can discuss the exact same location. Now, this doesn't, it's a quirk. You just know it happens, and so you can know that there are multiple ways to write down the same thing, but you don't let it bother you too much. You just have to understand that that's just the nature of this coordinate system. Because it uses angles, you can change how the coordinates look and get the same location. So normally you kind of restrict yourself to force the angle to be between 0 and 2 pi after that. But if it goes outside of this, you just understand like how it would work. You just keep measuring the angles as you usually do. So r comma theta is going to be the same as r. So I'm looking at right here. So r comma theta is going to be equivalent to r comma theta plus 2n pi. Any multiple of 2 pi that I give you added to the angle, it's actually going to not change the location. It's going to be the same place. Now, there's another thing that's kind of strange. It turns out that your r itself could be a negative number. And so that's the thing that I mentioned, oh, that's kind of seems confusing or counterintuitive or something. But again, if you think of negative here as changing direction, then it actually makes sense. So yes, r, we normally think of it as a distance from the origin, but it's not like a positive distance always. It can be a negative distance, but negative just means that you actually change the direction in which you measure it in. So instead of, so if I tell you an angle, instead of moving towards that angle, you would actually move in the opposite direction. So if my r was negative, I would just have the point down here instead, right? So it's just a matter of changing the direction. So just like how making theta negative changes me from measuring the angle counterclockwise to measuring clockwise, same way if r is negative, instead of extending towards the angle, I would move away from the angle, completely, like a complete 180, right? So that's what that would mean. So it's also possible for the r to be negative. So let's actually look at a very similar point here. We have 1 pi over 4. What would it mean for me to make the r negatives, like a negative 1 pi over 4? So it turns out that that just means a change of direction. So I can be like here, and I could be like, all right, here's pi over 4, and I want to extend 1 unit, and we know that that is 1 pi over 4. What negative 1 would mean is that instead of moving towards the angle, I would move away from the angle. Again, I would still measure 1 unit long, but I go in the complete opposite direction of pi over 4. I essentially move by pi over 4 plus pi, like I do a complete 180. So this will be the point, -1, pi/4. Right. So you move in the opposite direction. And so you can get all sorts, so you can note. So like me writing -1, pi/4, it will be exactly the same as saying 1, 5 pi/4. Or it'll be the same as -1, 9 pi/4. Right? Or it'll also be the same as saying 1, 13 pi/4, etc. Right? These are all different ways to write the same point, you know, equivalent to a bunch of other stuff. Right? But negative just means you go in the opposite direction. Any questions on that? Right, so yeah, I did that. That's where memory was coming from. So if I were to do like 1, pi/4, right? So like this guy means I move pi/4, extend out 1 unit, and that is 1, pi/4. But then I could also do 1, 9 pi/4. Just add another one, just so I go around I would actually end up here. So that's 9 pi/4. And again, I extend 1. I would end up with the same spot. Then again, I could do 5 pi/4, which brings me around here. But instead of going towards 5 pi/4, I go completely the opposite direction. Again, that's 1, and I end up at the same spot. So this is where they would all end up if I rewrite things multiple different ways. So there's going to be an infinite number of ways to actually write down any one location, right? So that's a quirk of this coordinate system, but having this new coordinate system, trust me, the benefits outweigh the drawbacks. But this is actually an important one that you have to remember, right? So the sine of theta is interpreted the same way as you would in pre-calc. So when it's positive, it's measured counterclockwise. I actually don't know which way the video is doing it, but hopefully my hand is moving counterclockwise. So when the angle is positive, you move counterclockwise. When the angle is negative, you move clockwise. If your R is positive, you move towards the angle. If your R is negative, you move away from the angle, as in going completely 180 of where you think you should go. Oh, yeah, so the video mirrors it. Yeah, so sorry about that, but I'm saying what it should be. So it's counterclockwise for positive angles and clockwise for negative ones. And we're going to take a quick break here, 5-minute break. And we will get back to this. So see you guys in a bit. All right, so we're back. So we saw how to measure things in the polar coordinate system in terms of finding locations of points and the fact that the points, they don't have unique addresses. So there's an infinite number of ways to write exactly the same location. And so that might seem a little bit annoying to you, but it's really understood once you get used to it. You might also notice that, you know, I started talking about polar coordinates, but we're starting very simple, starting from the geometry and building our way up. And other than this, the arc length thing that we did at the beginning of class, there's not going to be any more calculus for this class. It's all going to be very basic geometry-based kind of stuff. And so that's all we have planned for today. So taking a break from the calculus. But yeah, let's actually start talking a little bit more about some basic things. So we know this, and this comes from trigonometry. This looks weird. These two things. And the idea is the following, right? So good old trigonometry can help us out here. So let's assuming that I can locate a point with an angle theta and a distance from the origin r. then of course I can play that whole game of making this into a right triangle. And of course, the length of the vertical component is going to be r sine theta. Notice that that's going to give you the y, right? That's going to give you the height on the y-axis. Let's say I call that y. And similarly, if I look at the horizontal distance, this here, that is r cosine theta. And of course, that would give you the x, right? So whatever is located here, that gives you the x coordinate, right? So we have that intuition from trigonometry. And so we have the following, right? So when we look at the r and the theta coordinate, it turns out that we can relate this to the x and y coordinate in a very natural way using our trigonometry intuition, you know, the SOHCAHTOA kind of thing. And we can use these relationships to kind of convert from one coordinate system to the other. So I mentioned there are a bunch of situations in which working the polar coordinate system is nicer. So it stands to reason that you'd probably not be in the polar coordinate system, then you have to transfer things to the polar coordinate system to work it out, and then you transfer them back. So we need to know how to actually do that. So we use trigonometry to develop these equations. So to go from the r theta world to the xy world, you can use these equations. If I know the r and the theta, I can figure out the x and the corresponding x and y coordinates, because x will be r cosine theta and the y would be r sine theta, right? I also know that because the point xy lie on a circle of radius r, that x squared plus y squared equal to r squared. And I can, using this triangle with SOHCAHTOA, if I want to find the angle, I can just use the arc tangent. Or sometimes people like to use the arc's cosine or sine, or depending on the situation, because tangent has these discontinuities that sometimes people don't want to worry about. So you can actually use theta as the cosine inverse, right? So we see here that cosine is x over r, which, by the way, is adjacent over hypotenuse, if you're paying attention to the figure. And the sine of theta is y over r, which is opposite over hypotenuse. So you can actually do that. So this is going to be cosine inverse of x over r, or sometimes you can even think of this as the sine inverse of y over r. Right? But it's just other ways of finding the same thing. And that's because sometimes if your x is like 0 and you don't want to have to worry about division by 0, it actually works out in this equation. And so you can actually figure out what that is. And so sometimes it's complicated to use the tangent. So you can think of them in terms of sine and cosine, but generally speaking, the tangent inverse is a way that we can look at this. And these two equations, these are useful from going from xy to r theta. So if you're in the rectangular coordinate system and you want to convert things to the polar coordinate system, these equations work on a coordinate by coordinate basis. These equations specifically work on a coordinate basis. If, on the other hand, you want to move from the polar coordinate system back to the rectangular coordinate system, then these equations become useful on a coordinate by coordinate basis. Right. So this is definitely something I would want you to memorize. Right. So these are just equations that we know now. We know how to convert from one to the other. Right. And that is something that you should know. And it's definitely something I'm going to be testing you on. So let's actually do some examples. Right. So let's actually convert some coordinates. So here, I want to change the points r comma theta equals 2 comma pi and r comma theta equals radical 3 comma pi over 6 to rectangular coordinates in x comma y. Right. So I want to go from measuring things in a polar coordinate system to being in a rectangular coordinate system. Right. So for, you know, r comma theta equals 2 comma pi. So remember, I can find x by doing r cosine theta. And I can find y by doing r sine theta. Right? So using these two equations here. So my r is 2 and my theta is pi. Cosine of pi is -1. 2 times -1, that's -2. My y would be r sine theta, so that's 2 sine of pi. Sine of pi is 0, so that's 0. So this would mean that the xy coordinate is just -2, 0. So if I were to graph this, the point would be over here. -2, 0. Right? And that's in the rectangular coordinate system. Move 2 units left from the origin and 0 units up or down, and I would get that point. But also notice that this would be exactly the same point I would get by moving at an angle of pi and then extending from the origin a distance of 2 units. Right? I would actually get the same location. So those two are equivalent. So r comma theta 2 comma pi is equivalent to the rectangular coordinate -2, 0. So this location in the polar coordinate system 2 comma pi is equivalent to -2, 0 in the rectangular coordinate system. And remember, this is a unique address, right? So while there are multiple ways to write this down in the polar coordinate system, there's only one way to write this down, right? The second coordinate has to be 0. First coordinate has to be -2, right? It's a unique address. So that's that. Any questions on this part, the conversion? Just comes down to remembering these equations. And you apply the first pair if you want to go from polar to rectangular. And you apply the second pair if you want to go from rectangular to polar. And this you can do this on a coordinate by coordinate basis. And we're going to generalize some of this swapping coordinate systems in a little bit. On a coordinate basis, you can do that. Let's do the other one. So we also had r theta equals radical 3 pi over 6. And I mean, obviously this is not going to change much. So your x is going to be r cosine theta. Your y is going to be r sine theta. And so this is radical 3 cosine pi over 6. This is radical 3 sine pi over 6. Pi over 6 is the first column. Sine is 1, 2, 3. Cosine is 3, 2, 1. So the sine is a half. And the cosine is radical 3 over 2. Which is also, this is 3 halves, and the sine is radical 3 over 2. So this would mean that the xy coordinate of the same point is going to be 3 over 2, comma, rad 3 over 2. And so and all the points I'm plotting, you can conceptualize them as being in the xy plane, whether I'm using theta r or xy. I'm always drawing these in the xy plane. We're going to notice the difference between the theta r plane in a little bit, and that's actually going to be useful in a little later. But yeah, so you move 3. You move 3 over 2 here, and then rad 3 over 2 there, you get this point. But again, that would actually be the same as moving at an angle pi over 6 and then extending to a distance radical 3. And you can actually check that Pythagoras' theorem would hold for these numbers, and everything would actually work out. So that's that. That's it. Nothing really. Any questions on these conversions? Are we okay? We can do the opposite. So normally, if I write coordinates, it'll be assumed that they're in the x and y. Because the polar coordinate system is new, I'll generally just actually specifically identify them. So I'll say r comma theta equals this coordinate. If I just write a coordinate, the assumption is it's x and y, right? Because that's the usual way that you've thought about it in your lives up until this point. Pun not intended. So for 1, 1, how do we do this? So this is this guy, 1, 1. So we know that kind of lies on the line y equals x. So we would expect that the angle is pi over 4, and we're going to realize that it is. But yeah, so that's how we're going to do this. So for this, the second pair of equations become useful. So we know that x squared plus y squared equals r squared. Right? And by the way, that should be, there are a lot of times students actually go through the calculations and they would say, oh, x squared plus y squared, and then they'd plug in, you know, the r cosine theta squared plus the r sine theta squared. And then that's just r squared times cosine theta, cosine squared, plus r squared times sine squared. Then they'd factor out the common r. And they say cosine squared plus sine squared is 1. And then they finally get this. And they're doing this while they're working on another problem. They take like 4 extra lines to do something. Now, you should just know that x squared plus y squared is r squared. Just immediately have that in your mind. It's just something that you should know, and I would expect you to know, and I don't ever expect you to actually write that out. There are times when you need to actually write these out, but not in the x squared plus y squared scenario. Like if I gave you x cubed plus y squared, okay, then you kind of write things out and see what you have. But x squared plus y squared, you should just know it's r squared, right? That's just what it is. And so that's what we're going to do here. So to find the r, I can use x squared plus y squared equals r squared. So here I have x squared plus y squared equals r squared. This means 2 equals r squared because my x and y are 1. So I have 1 squared plus 1 squared equals r squared. And so here, now you'll see a very natural way that just through computation, the possibility of a negative r comes into play. There's a negative radical 2 and a positive radical 2. And you might think, oh, r is a distance. Why does it look like this? Yeah, don't freak out. The negative just means a change in direction of how you're measuring the distance. Okay. So this is just saying it's possible to actually write this angle in 2 ways, where the r can either be a positive radical 2 or a negative radical 2. So now we would go to the theta, and we know that our theta is tan inverse of y over x. And remember here, I know what the x and y are. They are 1. So this means this is the tan inverse of 1, which we actually know is pi over 4. Right? Now, technically, you can do plus for tangent, it repeats every pi. So plus k pi to get more representatives. But for the most part, we're going to ignore this and just take the pi over 4. And so that is actually just one way to look at it. So this gives this idea here. That I could move at an angle of pi over 4 and extend a distance of positive radical 2. Or I can move at an angle of pi over 4 plus pi, which would actually be one of the solutions that would work out with a tangent to repeater's value every pi. And then, so this is pi over 4 plus pi, which is 5 pi over 4. And instead of extending in this direction, I would extend in the opposite direction by a radical 2 magnitude. And that will give me this. So in both cases, I would get the same location. So I would get r comma theta is equal to radical 2 pi over 4. This is equivalent to my x comma y being 1 comma 1. And here I have r comma theta is equal to negative rad 2 comma 5 pi over 4. And it's equivalent to x comma y equals 1 comma 1. Okay, so we can have that. I don't know if there are any questions on that. So it's like not, so we're going to move on. So here, let's move on to the next one for, I think it was 0 comma 2. Yes. Okay, so this we actually know. Zero comma 2 would be straight up here, right? 0 comma 2. So we know that x squared plus y squared equals r squared. This would mean that 4 is equal to r squared. So your r is equal to plus or minus 2. We also know that theta equals, so we've imagined this as the tan inverse of y over x, but you'll notice that that's undefined here. Now, there are a couple ways you can actually look at this. We actually know exactly where tangent is undefined. So by getting an undefined answer here, you can automatically know that the answer is some like k pi over 2, where k is odd. Like you can actually know that, and then you can take pi over 2 equals theta, right? So you can just know that from the fact that tangent is, the tan inverse is undefined. Because it's at a point where it's like dividing by 0. We know that happens when the cosine is 0. Cosine is 0 at odd multiples of pi over 2. Or you could actually just use one of the other ones. So this is a scenario where someone might see that and they might freak out because you're doing y divided by x, which is 2 divided by 0, and that doesn't make any sense. So you could use one of the other versions. You could use something like theta is equal to the cosine inverse of y over r. And now you actually know what the r is. Sorry, this should be x over r. And so it actually doesn't matter what the r is in this case, it's just cosine inverse of 0. And we know that that's going to be pi over 2. And you can get plus 2k pi for others with positive r value. Or you could do something like a minus pi over 2 plus k pi for negative r values. So I'm just using reference angles, essentially, just to, you can rewrite the angle in multiple different ways, but you just pick one and you would be fine. So here, one way to do this is to think of your theta as pi over 2, which that's straightforward. That's just 90 degrees. And extending a distance of 2 units. And that would get you this point, which you'll notice will be the same one. So this is 2 comma, this is r theta equals 2 comma pi over 2. I could also do something like negative 2 comma minus pi over 2. Now, there's something that I could talk about here, and this is just writing down what we call all representations of the polar coordinates. So I can say all possible polar coordinates. Right. So this is something that I might ask you, so let's pay attention to that. And it's just writing down the generalized form. So I could do something like r theta equals 2 comma, what was that, pi over 2. So I could do something like pi over 2 plus 2n pi for n, any integer. Or I could do something like r comma theta equals minus 2. And I could do something like 3 pi over 2 plus 2n pi for n, any integer. So that could be this scenario. So I can write down all possible ways to write this down with a positive 2, and I know I can go at an angle of pi over 2, but then every time I add 2n pi to that, I get back to the same place. Or I could go 3 pi over 2, which brings me to the negative, and go negative 2 to flip back up. And that angle, I can just keep adding 2n pi. So this is just a way of writing down all representations, which from time to time I might ask for. And I think I asked for that at some point. I can't remember if that was both for the practice test and the test, or just the test, or just the practice test. But I remember writing down a problem like that. So you should know that. But again, it's not even calculus. It's just like, trigonometry, knowing how reference angle works, knowing that when you add 2 pi to something, to an angle, you kind of end up in the same position. Yeah. Okay, so now we're going to talk about, so that was how we can convert from one to the other. And it really just uses these sets of equations here. So basically it's just some simple calculations. You can use the first two to convert from polar to rectangular, use the last two to convert from rectangular to polar. So now we're going to see one of the main ways in which polar coordinates can make things useful and simpler and easier, and that is just to be able to describe regions in the plane that are of a certain nature. So let's look at describing these things. So I'm just going to jump in with some examples and we'll just kind of explain how they go. So I could describe a region in polar coordinates. So let's say I want the region in the plane that's bounded by the quarter circle in the first quadrant and the positive axes, right? So I have So I have a circle. And the circle is of radius 3. But I particularly care about this region, right? The part that's in the first quadrant. So this region here. Okay. And so now what I want to do is I want to describe this in terms of polar coordinates. So we know we can actually describe this in rectangular coordinates. So to describe in rectangular coordinates, here's what we could do. We can say, all right, we see the x values of this shaded region. They go between 0 and 3, right? So there's a 0 right here, and there's a 3 right there. So everything we care about happens between x's between 0 and 3. Cool. So I can actually write this down as an inequality. I only care about x values between 0 and 3. That will cover this entire shaded region. Now I want to think about what are the limits on the y, right? So, and this is something that you're going to do again in the next class a lot more, is you can describe a region in xy by actually thinking of the x, one of the variables, in this case I'm thinking of the x, as going between constants, just some length on the interval. And then the other one I can think of as going between functions. So I think of it as a higher dimensional thing. So when I'm thinking of y now, I'm not thinking of intervals, like, because I can't just put, say, 0 to 3 as well. Because if both x and y go from 0 to 3, and it covers everything from 0 to 3, I actually get a rectangle, right? So if I'm taking all x's between 0 and 3, and then all y's between 0 and 3, I get all possible coordinates here, which is not what I want, right? I only want to get the circular part. So what I can do is I can bound y between curves instead. So I can say my y should go from this function, which is this horizontal line on the x-axis, and then it goes up as far as it hits this function, which I actually have the equation for. So I think of x as going between constants and the y's as going between functions. And so the y I can describe as the following. It's all y values between the line y equals 0 and the curve y equals the positive radical of 9 minus x squared. So that is one way to describe this region's inequalities in terms of the set of all x, y in this region, right? So this describes the set of all x, y's. Any questions on this, on how I actually figured that out? Or it's because I know the upper semicircle, the equation of that, I just went here and I solved for y. So of course I get a positive and a negative, but the negative is the bottom. So I ignored that and I just put the top one. So it's described like this. So here you can see in terms of the rectangular coordinates, it's not anything crazy. However, you should notice that my y is between this whole radical function, and for various reasons, a radical function can be very, very annoying to deal with. I mean, just think about like if I had the integral of this, right? to think of this without a radical versus with a radical, like the first one is the power rule, easy peasy, no problem. The second one, I can't use substitution because there's no factor of x. I'd have to go through a whole trig sub to do this integral, right? So just having a radical of that expression can be very annoying in certain contexts. Like in the integral context, it is super annoying to have a radical over the 9 minus x squared, okay? So it doesn't look terribly crazy, but clearly we now have some appreciation of how crazy things like having a radical could make things. So let's actually look in polar, but in polar coordinates. The set of all r comma theta in the region. Now remember, this is a circle of radius 3. R measures the distance from the origin. What is the distance from the origin? Well, it's literally always 3, right? The set of all points in this region is the set of all points that can be from 0 units away at the origin, which means it's the origin itself, and it can extend as far as to 3 units away from the origin, which means, hopefully I have enough undos to undo this, which means my r, I can just think of it as going between constants. My r can range from 0 units away from the origin all the way up to 3 units away from the origin. Okay, cool. What about the angle that covers this region? Well, I can be anything from 0 radians from this, to the shaded region described by 0, all the way up to pi over 2. So I can measure angles from 0 opening up to pi over 2, and then I'm just extending distances from 0 to 3, and then I would get this entire region. So in other words, my theta, I can think of this as just take on all numbers from 0 to pi over 2. And so this is me describing that region in polar coordinates. Now, not only is there no radicals present, but there aren't even any variables present in these limit representations. I went from a scenario where I had to describe something as a radical function to a scenario where I can describe everything in terms of constants, in terms of numbers, right? So in the r theta universe, so I mentioned that we've always been drawing in the xy universe. So this here is the xy universe, which is a circle, a part of a circle, right? However, in the r theta universe, the region I'm describing is actually a rectangle. Universe. If my theta is the horizontal, my r is the vertical, I'm really just describing anything r goes from 0 to 3, theta goes from 0 to pi over 2. So it's a rectangle. And you're going to learn, and this is something you'll really appreciate in starting in Calc 3 and above, that sometimes being able to visualize in terms of rectangles is going to be useful. There are a lot of things where theoretically we set it up based on rectangles. The integral, for example, is such a thing. We measure Riemann sums in terms of rectangles, right? And so similarly, we're going to do higher dimensional integrals in terms of boxes, which is just a rectangle extended for a certain length, like a prism, right? So a lot of things, when you can think of them in terms of rectangles, they're going to be a lot easier to deal with theoretically. Our formulas is already set up based on rectangles, because we set up a bunch of things when we were in the rectangular coordinate system, and a lot of tools that we already use, they were set up for the rectangular coordinate system. But there are times in the rectangular coordinate system, as a result of just how it behaves, gives us something complicated. But then if we switch coordinate systems, ironically, we can end up with a rectangle in a scenario where we didn't have one before. And it's actually easier to deal with in this scenario. And I mean, you can just look at just how it's written down. It's clearly easier, right? So here it's like, integral of a constant versus integral of a radical function. It's going to clearly be easier, right, in some contexts. Okay, so this sort of gives you an idea of how polar coordinates can start to simplify things, right? So we can keep going. So let's actually go and describe some other region. So there's a type of region that's pretty common. It's called an annulus, which it looks kind of like a washer. I don't know if anyone's going to know what a washer is. It's pretty much like the area in between two circles that have the same center. We call that an annulus. For example, we can talk about the region in the plane that is described by all points that are for which x squared plus y squared is less than or equal to 9. So let's see what that would mean. So we can have this, and we know x squared plus y squared equals to 9 is just a circle of radius 3, right? So x squared plus y squared equals to 3 is this circle. But of course, that's when you're like the radius is 3. But if you want the entire region, like what if you want something that's a distance of 2 away? That's less than 3. So less than or equal to 3 just means you're looking at everything inside the circle, right? So it's not only just the boundary of the circle, but it's also the insides filled in. But at the same time, we want to look at x squared plus y squared is greater than or equal to 1. So inside of this circle of radius 3, there's a circle of radius 1. I want to be outside of this circle. I want to be bigger than, farther than 1 distance away, and smaller than 3 distances away. So I get this this little region in here. Right? This region is called an annulus. Okay. So it turns out now we can start to describe this in rectangular. Well, actually, let's do it in polar first. So let's do in polar. So what do I want for the R? Well, R is just a distance from the origin. So the shaded region between 0 and 1, I do not care about. So I would start measuring my R at 1. Nothing starts happening before I'm 1 unit away from the origin. Prior to that, it's just empty space. So my R can go from the radius of 1. But how far would it go? So I would start at 1, and then I can go as far as a distance from 3. So at any given point, I would start at 1 and then extend as far as 3. Start at 1, extend as far as 3. And that will happen no matter where, what direction I want to measure this in. So R goes between 1 and 3. My radius can go from the 1 radius circle all the way up to the 3 radius circle. What about theta? Well, theta, the shaded region is going around the whole thing. So that's just 0 to 2 pi. Again, you'll notice that that is a rectangular in the polar coordinate universe. If I were to graph R versus theta, that would be a rectangle. And so that is how you would do it in polar. Now, what would it look like in rectangular? Well, that's a little tricky, right? So you sort of have to describe it in probably a couple different ways. So you can describe it, you'd kind of have to split it up. So here we're already seeing, because in the R theta, we're thinking in 2 different universes, right? So we're thinking up and down. So you probably have to think of this here, where the y can go from this curve all the way up to that curve. But on the inside, it'll go from this curve all the way up to that curve. And then over here, it'll go from this curve all the way up to that curve. So we can probably split it in two because the equation for this side is the same as the equation for that side, right? And the equation for this side is same as the equation for that side. So we can probably do that both at the same time. So I would say something like maybe I shouldn't do this. Can I go all the way back? Okay. It's okay. Okay. So I can talk about for x between 1 and 3, or x between -3 and -1, I would have my y can go between this circle. So it's the -9 minus x squared to positive 9 minus x squared. Okay, now between 1 and -1, so it's already getting a little complicated here. So there's a possibility of y going from, if we're looking at the top part or the bottom part. So our y can go between go between positive. Our y would go between the positive radical of 1 minus x squared up to the positive radical of 9 minus x squared, or it can go from the negative radical of 9 minus x squared up to the negative radical 1 minus x squared. I mean, it's a whole mess, and it's not even clear exactly what that even means. Like, what do you mean for x between minus? Because then it's like you'd have to say, oh, there's an upper part and then there's a bottom part, and you know, like both of them would occur between x is -1 and 1. There's probably a way for you to write this in terms of absolute values and kind of put this all together. And so you can say like, oh, the absolute value of y is between this and that or something. But it's like, either way, come on, yuck, right? Like, look at this versus having to describe a curve to this. And this, you'd probably like need a whole instruction manual for like how to read the thing. Like, oh, this is what I mean when I did here. And I split these into these two things. Like, how are you going to describe this region by up or down or top or bottom, right? Why going from something up to something else? Because it depends on where you are. Like out over here, it's y goes from this vertically up to that. But over here, it's a completely different thing. This vertically up to that. And that part is not even actually done. You'd have to describe from this vertically up to that, which is what I did here. And then you'd have to describe this vertically up to that, which is what I did here. And it's like, just talking about what this region would look like. I mean, come on. Like, I just want to talk about a very simple object called an annulus. Like, I want to just say, I want the region between two circles, right? Like, to describe that idea in rectangular coordinates, using inequalities. Seriously, come on. In polar coordinates, easy peasy, right? Now, when you're doing calculus and you're going to be taking derivatives and integrals and stuff like that, I mean, using this versus using that, I think there's a clear winner here, right? There's like, I don't have to think which one I would want to do that. Like, yeah, obviously I want to work with that one, right? So you can see that polar coordinates, they can, and here I'm not even doing any math. I'm literally just describing a region where I want to do the math, right? And it's already getting messy with rectangular coordinates. So you can imagine when you actually start doing math and calculations and calculus, like it can get really bogged down in rectangular coordinates for a region like this. Whereas with polar coordinates, the region is essentially rectangular, right? Everything we know about a rectangle, we can apply in polar coordinates, right? So our integrals will be set up to deal with things very well in the polar situation versus the rectangular situation. So here you're seeing there's a lot of benefits, you know, to being able to think in polar coordinates. Let's look at another region. And again, I'm sort of, so I can explain this in words, right? The region in the plane where I want my y greater than or equal to x and my y greater than or equal to minus x at the same time. And I want x squared plus y squared to be less than or equal to 1, right? So this is me using words, right? Not even just straight up inequalities. I just want to use words. And then I actually want to describe. So let's actually draw this region first. And we'll realize that this would look like, so let's look at y equals x. So that's this line here. And y equals negative x would be this line here. These should go through the origin, by the way. This is y equals minus x. And then we have the circle of radius 1, which is this guy here. This is x squared plus y squared equals 1. So what did we say? We want y to be greater than or equal to x, which means when I'm looking at the y equals x line, I want to be above that line. I want to be in this direction. I want to always be on top of that line. Now, at the same time, I want to always be on top of this line, the y equals negative x. So obviously that now restricts me to this area over here, right? That's the only area that works for both of those restrictions. So nothing down here will work for this guy, and nothing over here is going to work for that guy. So I'm left with that region up there. But now I want this requirement that my x squared plus y squared is less than or equal to 1. So that pretty much means I need to be within this circle. So that leaves me with this region right here. Right? This is the region I care about. I want to describe this region in polar coordinates. Right. Now, we know that y equals x and y equals minus x. Y equals x goes at pi over 4 degrees to the positive x-axis. Y equals minus x goes 3 pi over 4, not degrees, radians from the positive x-axis. So in polar, my r is going from a distance of 0 to 1. My theta is going from an angle of pi over 4 to 3 pi over 4. Again, I can describe this scenario with a rectangle. And normally, and I mean, just to kind of give you a hint as to, in the future, when you're going to want to actually care about this, is if the region you care about is a part of a circle centered at an origin, like some slice of that circle or a sector or a segment of that circle, polar coordinates is going to be a lot more useful to describe that region than rectangular coordinates. That's sort of the basic idea. If you can dissect the region you're looking at as like in terms of circle centered at the origin, you're going to want to switch to polar. if your circle is not centered at the origin, polar can make things a little bit easier, but it does its best work when the circle is centered at the origin, right? And again, that's because it's based on x equals r cosine theta, which we know when we're studying parametric equations is a standard form. When x equals r cosine theta, y equals r sine theta, that's the standard parametric form of a circle centered at the origin, radius r. So the polar coordinate system is kind of set up in that framework. If I'm looking at rectangular here, I would have to say something like, I would repeat some of these. Y must be greater than or equal to x. I need my y to be greater than or equal to minus x. I want these two things in general. And I want, oh, well, I'm actually going to have to split this up a little bit, because I'd have to describe this part, because I want y to go from the x up to the circle. And that has to look different from this part, because I want y to go from the minus x up to the circle. So, and then, so then I would need my y to be, I think I can do both at once, but it's still going to be very annoying. So I can say, all right, I want y to go between x and radical of 1 minus x squared, but I want that to occur between x goes from 0 out to 1. And then I want my y between negative x and the radical of 1 minus x squared. This will occur for x goes from -1 to 0. And not even, this is going to be, it's not 1, because this would come down to something that's less than 1. So it's actually even a little more complicated. So the hypotenuse is 1. But I know that these two are the same. So it's like I have a pi over 4 here, and there's a and there's a 1. There's a 1 here, and I want to know what is this distance here, which is my x. So I can use say cosine of pi over 4 equals opposite over adjacent. So x is equal to r cosine theta, and so that's rad 2 over 2. And the other one would be like minus rad 2 over 2. So we went from a scenario where I could just eyeball things and know them to like, now I'm literally having to like set up triangles and solve for angles to figure out what region am I looking at here exactly. So if I were to just describe the region in terms of nothing but inequalities, that's what it would look like compared to just these guys going between constants. So you can kind of see that polar coordinates does make things a lot easier in terms of certain regions. I can do another region. X squared plus y squared less than or equal to 16. Again, this is just a circle of radius 4 centered at the origin. And I want everything inside of it. Right. So in polar, again, my r is just 0 to 4. My theta goes from 0 to 2 pi. again, just using constants to describe it. If I wanted to describe in rectangular, I could say x goes between -4 and 4, and my y goes between positive radical 16 minus x squared, negative radical 16 minus x squared. So, yeah. Polar coordinates is nicer, right? And this is just in descriptions. Like, you have no idea, like when we actually start to do like calculations and integrals based on regions and iterated integrals and all that, like it's a significant difference to have to worry about something being the radical of a 16 minus x squared as opposed to just a 2 pi or a 4 or something like that. Like, it's going to make a big difference. And yeah, so that's just giving you a taste of how convenient polar coordinates can be. Right. So we know what polar coordinates are. We know how to convert between polar coordinates and rectangular coordinates. And we learned the equations for that. And we know how to use polar coordinates to represent certain regions, and the fact that it can be very easy to do that in comparison to rectangular coordinates. Yeah, so next we're going to look at sketching polar curves. But that is after the break. And I mean, hopefully it can wrap up everything we want to do today. But the next thing I want to cover, I don't think it should be too bad. I can probably even rush even faster than I'm doing this, but we'll see. So we'll take another 5-minute break here, and I'll see you guys back in a little bit. All right, let's continue. So we now know, let me check here. So we now know how to describe regions in polar coordinates, at least for circular regions, which would be what I would test you on for this thing. Let's actually go into sketching in polar coordinates. So it turns out we can get some very interesting sketches in the polar world if we give a formula in polar coordinates, things that it would be very hard to describe in terms of x's and y's. And so we're going to look at some such things now. And again, we're just going to kind of jump in for now and try to figure things out on the fly. So you look at something like sketching the following curves in the XY plane, right? So you'll need to know how to sketch curves and how to pretty much match curves, identify a curve that's drawn. So we'll start off with this curve, like r equals 1. What does that mean to sketch the curve r equals 1? So this comes down to you remembering what the r and the theta should represent in polar coordinates. So remember, r is representing the distance from the origin, and theta is representing the angle made with the positive x-axis. So here, when I write down the curve r equals 1, and remember, curves are just an efficient way of telling you a lot of points all at once. When I say r equals 1, what that means is I'm talking about all points that are a distance 1 unit from the origin. So when I said me saying r equals 1 is like me saying I want all points that are 1 distance away from the origin. And of course, what does that remind you of? A circle. It's literally a circle. So this will be true for all theta. Theta is not specified. So for all possible thetas, I want the distance to be 1 unit away from the origin. And so this is just the equation. This is just a curve. The curve is a circle. So maybe I should write that down. So conceptually, this is the set of all points 1 unit distance away from the origin. And so you could actually figure out that this is just going to be a circle of radius 1. That's all points that are 1 unit away from the origin. This is graphing in the XY plane. Now, conceptually, that's what it is. You could actually figure this out formulaically as well. Because not all the time you're going to be able to look at a polar curve and just, oh yeah, it's conceptual. I can see, right? Like you can't always do that. But if you can actually figure things out from the equation just by looking at it, you can actually go back through those equations that I showed you earlier that allows us to transform from one coordinate system to the other. So for example, we know that r equals 1. This would mean that r squared is also equal to 1. Now, why would I care about r squared? Because I know that r squared is x squared plus y squared. Right. Since r squared equals x squared plus y squared. And that is clearly a circle of radius 1 centered at the origin. Which again gives you back why my thing is becoming unsynced. We'll work out later. Right. So you can do this conceptually, or you can go through the formulas, and we're going to, we can do both. So knowing those formulas, knowing that r squared equals x squared plus y squared, knowing that x equals r cosine theta and y equals r sine theta, that'll be a very useful things to know, not just in terms of converting, but in terms of looking at the actual curves that you would want to draw. So another one, let's say theta is pi over 4. And again, we can look at this conceptually. Like conceptually, we know what this means. This is all points that are at an angle of pi over 4 from positive x-axis. Okay. Now, of course, there are going to be two sides to this thing because your r is not restricted. They never tell you that your r has to be positive or negative. So it means that you can have pi over 4 and all positive r's going off to infinity. Or you can have pi over 4 and all negative r's going off to negative infinity. Either way, leads to, this is just the equation of a line. So this is literally another way of writing y equals x. Right. So the line y equals x is just equivalent to me saying theta is equal to pi over 4. Right. And you can even do this formulaically if you want. So my theta is equal to pi over 4. I know that that means that tan inverse of y over x is equal to pi over 4. But that would mean that tangent of pi over 4 is equal to y over x. But what is tangent of pi over 4? That's 1. So this means that your y equals x. Right? So you actually get that. And this is, of course, you have to worry about when your x is 0, but you can deal with that case separately. And, you get a line. So getting a line at a certain angle, passing through the origin, is just a matter of me telling you theta is whatever angle I want. And that creates a line, right? So this is actually the equation of a line in polar coordinates. The equation of a line in rectangular coordinates is y equals mx plus b, right? That's for a non-vertical line. This is the equation of a circle in polar coordinates. It's just r equals a constant. The equation of a circle in rectangular coordinates is x squared plus y squared equals r squared, right? Where r is going to be the radius. So just theta equals r equals a constant is a circle. Theta equals a constant is a line. Let's actually look at something a little bit more tricky. Let's say I wanted to look at r equals secant of theta. Like what is that? Now that one is something that's less conceptual. What does it mean to be a distance secant of theta away from the origin? What kind of curve would that be? That's not exactly as intuitive as before. So this one is not as intuitive. So let's look at the formulaic way. So I want to take advantage of those formulas that I asked you to memorize earlier, right? So I'm going to be looking at these guys. Okay. So this it's difficult for me to know what this is in polar coordinates. So my idea is, hey, maybe if I convert it to rectangular coordinates, something is going to stand out to me. So let's actually try that. So secant is 1 over cosine. I want to write it in terms of cosine because that's the language that I know from my equations. My equations don't have secant in it. They don't have tangents in it. They don't have anything in it but the sine and cosine. So I'm actually going to want to look at the sine and cosine. So what I can do is here your r is just 1 over cosine, which means r cosine theta is 1. But hey, r cosine theta is x, right? This here, r cosine theta, that is x. X is r cosine theta. So this is just a line x equals 1. So a vertical line is that. This will be at a distance secant theta away from the origin. Right. So this shows you like an opposite effect. If you want to graph straight lines that are not passing through the origin, they're kind of difficult in the, they make the polar coordinate a little bit more difficult than it would be in rectangular coordinates. So in rectangular coordinates, this is just x equal a constant. But also notice that it's undefined in the y equals mx plus b sense. However, in polar, it's actually a secant. So this is what the secant polar function looks like in the xy plane. So if I ask you to sketch the polar curve r equals secant, that is what you would sketch. It's a vertical line. Another common type of example. R equals 2 cosine theta. And by the way, we can generalize this to r equals some constant times cosine theta, or r equals some constant times sine theta, or generally speaking, r equals a constant times cosine plus a constant times sine. These would all be dealt with similarly. For one, again, it's not very intuitive what this would actually look like in the polar sense. So I'd actually try to convert this to something where I can look at rectangularly what it would mean. So if I look at, say, r equals 2 cosine theta, what I could do is I could say r squared is 2r cosine theta. I know because I want to get something like an r cosine theta. I see cosine theta in polar. I'm usually going to want to try to get an r cosine theta because I know I can translate those to x. So what I did was I multiplied both sides by r. Now that gives me the r squared, which I know is x squared plus y squared. And 2r cosine theta, that's just 2x. So now, and this is actually something I wanted to talk about later today. I'm not sure I'm going to get to it, but I guess we will leave that part for the beginning of tomorrow. But on one hand, like, I want to finish it today, but on the other hand, it's not really a calculus thing. It's going to be some things I'll remind you about from that you should have remembered from pre-calculus. So should not be too terrible. But to figure out what to sketch for something like this, you'd bring the 2x to one side. You complete the square for the x. Which means you're going to have to add 1 to the other side. We'll talk a little bit more about this tomorrow, but that's it. And that is actually something that you do understand. That is the equation of a circle centered at 1, 0, radius 1. So that's what that would look like. So this will go up to 2, this will go down to 0. This is in the xy plane. And I guess generally, if you see something like r equals a cosine theta plus b sine theta, you can always go by multiplying both sides by r. So this would be x squared plus y squared. This would be a times x. This would be b times y. Then you would do something like move everyone to one side. Then you would complete the square. So this would be x minus a over 2 all squared. And so you'd have to add like an a squared over 4 on this side. And here it will be like y minus b over 2 all squared. So you'd have to add like a b squared over 4 on this side. So it'll be a squared plus b squared all over 4. And so that would give you the equation of a circle, right? You don't have to memorize this. I'm just kind of showing you the general manipulations you have to make. Don't need to memorize this. Maybe I should put that in red. But it's just giving you an example of the kind of manipulations you'll do. Don't need to memorize this. The fact that you can go from this to that. Like an equation of the first form in polar is always a circle of the last form in rectangular. Generally, I don't want to memorize things where you have like a straightforward process to get it if you need it. It's not like it comes up every day. It's something where if you're in that situation, you know what to do. Multiply by r, bring everything to one side, complete the square, you'll get like a circle type thing. And so that would generally be that. Okay, so now something interesting actually happens when you start to like mess with the angle. So if you were to have something like a cosine of 2 theta, right? Like 2 cosine 2 theta or a cosine of 3 theta or something like that. That starts to get a little bit trickier. It also starts to get trickier if you have something like a constant in the mix. Like r is now like 1 plus sine theta or something like that. So now you're at a distance of 1 plus sine. So you can be at a distance of 1 unit, but additionally you can go off like a sine. or reduced by a sign if it's negative, right? So you have sort of scenarios like that you'd want to be able to deal with. And so that leads you to the next set of examples. So these were just ones that you can either conceptually understand, or two, just through some formulaic manipulation, you can actually figure out the rectangular versions of the equations pretty easily. But another one that comes up all the time is, at least in Calc 2, this is we're kind of treading the territory where, you know, after Calc 2, you'll never really have to do this anymore. Maybe you'll be in a scenario where you need to recognize what's going on, but you're never going to need to do this by hand like I'm teaching right now. But you'll need to know it for this class. So when you look at things like these examples here, and I don't want to do all of them, I will probably do like 2 or 3 of these examples and leave the rest for your for you to try. By the way, I put the answers here. So look at that. Imagine being able to write down that equation in rectangular coordinates. It's going to be it's not even a function, right? It fails the vertical line test, fails the horizontal line test. So it's not a function at all. But that is something that you can actually get from a polar curve, like very pretty things like that. I don't know if that's one of the reasons why it's still in a Calc 2 syllabus, because you can make pretty pictures from it. And you'll probably appreciate those math jokes. When someone writes a math equation and when you plot it, it looks like a heart, or something that says, I love you. And they make jokes about, oh, this is when a math person talks. Never mind. Okay, so you can get some pretty interesting graphs from the polar form of something a lot easier than you could get from rectangular coordinates. Like you wouldn't even be able to begin to be able to plot this in rectangular coordinates, or even something like that. But it turns out when you switch to polar, you can actually plot very complicated graphs by hand pretty easily. So some of these, so those guys are what these guys are. And so I kind of want to wrap up by showing you how to plot things of this type. And hopefully by the end of this, you'll also be able to identify these. Like you'll be able to say, how would I know that D was actually this equation versus one of the other equations, you know? So yeah, so that's what we're doing now. Background information that you would need. You'd actually need to know how to plot these guys in just regular trig functions. Like if I ask you to graph sine of 2 theta, you know, y equals sine of 2 theta, you should know how to do that, or cosine of 3 theta, and etc. So I'm not really going to go over that in detail, but I did put one of my old pre-calc videos where I was teaching this thing, and starting at around minute 47 is where I started talking about how to graph transformed versions of cosine and sine. Yeah, so I think there's a bunch of space that I left here. Yeah, so let's actually start with let's start with A. Let's start easy. Okay, so A, so this is R equals sine 2 theta. Okay. So here's something you should recall. So when you're graphing these and you're like messing with the angles, or you're adding constants, and it has sines and cosines, you're probably going to want to do this method that I'm going to teach you. It involves being able to graph the trig function as is. So you want to graph it in the R theta universe, and then you can translate it to the XY universe. So I'm going to use this as an example. And it's useful to recall some things. Again, the video that I posted there has a little bit more information. But the quick matter of it is the following. So if I look at something that looks like y equals a sine k x minus b plus c, or y equals a cosine k x minus b plus c. So these are like transformed versions of cosine. So you can shift the angle, you can multiply the angle, you can add a constant, you can multiply the entire trig function by another constant. And this actually changes the graphs in predictable ways. So the magnitude of A is the amplitude B is called the phase shift. It's how you shift left and right. It's the horizontal shift. C is the vertical shift. If you take 2 pi divided by the absolute value of k, you get the period. And if you take the period divided by 4, you get the subinterval. Because sine and cosine comes in 4 sections, right? So if you're looking at like a sine function, turns out that you can imagine this on a grid. You can imagine a sine function on a grid that comes in 4 sections. Where in the first section, you go from the middle to the top. This distance here, by the way, that's called the amplitude, how much you go up and how, like the height of the wave, the amplitude of the wave, if you imagine this as a wave, right? So this is a lot of, the terminology here is also sort of a physics thing. And so in the first one, you go from the middle to the top, then in the second part, you go from the top to the middle, then the middle to the bottom, then the bottom to the middle. The period is the length here. And then period over 4 is going to be all of these guys. Now the vertical shift C is taking this graph and shifting it either up or down based on the constant that you're looking at. And of course, you know that if the A were negative, it'll just flip things upside down. So there are all these things that you should remember from transformations of graphs. But when it comes to trig functions, this is going to be very useful. So when I have, when I see R equals sine of 2 theta, I kind of think of it as 2 sine 2 theta minus 0 plus 0, right? To kind of fit it towards this thing. And so I'd be able to talk about what the amplitude is, all that good stuff. So I would know that the amplitude is 2, the phase shift is 0, the vertical shift is 0. I also know that the period is 2 pi over 2, which is just pi. And I know that my period over 4 is just pi over 4. Now, how does that help me sketch this graph? So I'm going to go in and I'm going to sketch this graph. And this is going to be in the r theta world. Right? So I'm not graphing in the xy plane yet. I'm going to use what this guy looks like to talk about what is the magnitude of r for any given angle. That will help me actually graph the polar function. So what am I going to do? So I know, generally speaking, I'm going to want to graph things between 0 and 2 pi. So let's say 2 pi is here. So you start at the, then ultimately the subintervals are going to be of length pi over 4. So I'm going to want to split this, split this, split this, split this, split this, split this, split this. And so these are all going to, so this is going to be pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and 8 pi over 4. Whereas 6 pi over 4, I can actually write it as 3 pi over 2. Okay, so, and also the amplitude, since I start at c equals 0, and then I would go up by 2. So this, you'll notice, and this, like if I was graphing it on the board, I'd write it as a broken line, because this is not actually on the graph. This is just using a grid to help me. But now I know that this creates a grid, and in every 4 sections, I'm going to have a sine function. In fact, I'm going to have a positive sine function. There shouldn't be a 2 here. So I know how the sine is going to behave. It's going to start in the middle, then it's going to go to the top, it's going to go to the middle, it's going to go to the bottom, Let's go back to the middle. It's going to repeat this pattern. So my sine function is going to do this. And this is where you get like, in the physics sense, 2 would be called the frequency. So it means you have like 2 sine graphs in the period where you would normally have 1. So it's 2 back-to-back copies of sine. So it tells you how like the wave is kind of speeding up or being compressed, and you talk about frequency, but we won't have to talk about that. But this is how you would graph that thing, right? So I expect you to be able to do this relatively quickly. So you should actually practice this a few times, and the video up here should tell you more about that. But you'll actually get some practice by doing these examples here. So that is the graph of sine of 2 theta. So now, how to actually use this to get to, so this is actually 1 because I had a typo before. So how do I use this to get to the polar graph? Well, here's the thing. So all these important values that you show up on the r-axis, these are distances from the origin. So your r can range from a distance of -1, which again, remember, it's a direction thing. It's not like a negative distance, or it can go up to +1. So this is just really mentioning distances from the origin. And so what you can do is you can take the absolute value of all the numbers that show up on the y-axis, and you can draw circles of these radii in the xy plane. So now I'm going to the xy plane. Now there's only 2 numbers here, -1 and 1. The important numbers are going to be the maximum, the minimum, and the middle. So the middle is actually 0 here, so you won't have to worry about it. So here, absolute value of +1, same as absolute value of -1. So a circle of radius 1 is the only thing I have to worry about. Now the circle is not a part of the graph. This is just like it's an aid, right? It's something, it's a skeleton that I'm going to use. It's not actually, it's a skeleton that I'm going to use to actually help me draw the graph. So if you're writing this on a piece of paper, this would be like a broken line or a very faint circle. So that's the first thing. The next thing is you're going to put in all these angles. So each grid, you're going to put in the angles for that grid. So there's the angle, obviously 0, which is equivalent to 2 pi. There's the angle pi over 4. There's 2 pi over 4. There's 3 pi over 4. There's 4 pi over 4. There's 5 pi over 4. There's 6 pi over 4. There's 7 pi over 4. And 8 pi over 4, which is 2 pi. So the blue lines, you would sketch this faint or broken. It's a guide. To help sketch the polar curve. Okay, so now once you have this, it's a matter of now going to this and seeing the distances and then drawing them on this picture here. So here's how you would actually do this. So we know by looking at the top graph, when the angle is 0, our distance from the origin, remember r is the distance from the origin, is 0. So we start here at 0, 0. Then reading this graph, notice that when we go to the angle of pi over 4, our curve is now at a distance, r is 1 when the angle is pi over 4, which means on the angle pi over 4, we're at a distance 1 unit away from the origin, right? So this means from here, I would go, boom. When I hit pi over 4, I'm at a distance 1 unit away from the origin. And we're always spiraling in kind of a counterclockwise fashion because that's how the angles would move. Now, notice that on this and here, when I'm at pi over 2, my distance from the origin is 0. So by the time I come back to pi over 2, I go back to the origin. And notice that I've just created one leaf of like that flower petal. I've created a single leaf, right? So I'm back at the origin. Now I move to 3 pi over 4. Now 3 pi over 4 is over here. However, notice that my r is negative, which means I don't go towards 3 pi over 4. I go in the opposite direction. I go away from 3 pi over 4 because my r is negative. So I know that when I'm at 3 pi over 4, I go away from it to hit here. Then I come back to 0 by the time I hit pi. So I'm now here. So I'm at the origin when I'm at pi over 2. I extend to -1 when I'm at 3 pi over 4, and I come back to 0 by the time I hit pi. Now, because my r value is -1, I go in the opposite direction of 3 pi over 4. I don't go towards 3 pi over 4. I went away from it. So now I'm back at 0 and I'm at pi. So I'm keeping track of what angle I'm at. Now notice at 5 pi over 4, my r is 1. And then I come back to the origin by the time I hit 3 pi over 2. So I go towards 5 pi over 4, a distance of 1 unit. Then I come back to the origin. Now I'm at 3 pi over 2. Now from 3 pi over 2, I would go to 7 pi over 4, but it's a -1. So I go away from 7 pi over 4 the opposite way. So I would go up to 3 pi over 4, hit 1 distance away, and then come back by the time I hit 2 pi. And so we have this graph here. All right. So that's kind of, so this is the actual polar graph right here. So the white curve is the polar graph. Okay. Any questions about what just happened? Or maybe I can do another example. I'll talk through it again, and then you guys can tell me if you have any questions. So since we're just learning, E is probably too complicated to do right now when you guys are just trying to get the hang of things. So let's do something moderately a little bit more complicated. B is going to be very similar to the example I just did. So I'll do D, right? It has a little loop thing in there. That should be interesting. So let's do D. D is 2 minus 3 cosine theta. Now again, I want to write things in a nice way so I know how to graph the trig graph before graphing the polar graph. So I would probably want to rewrite this as -3 cosine, I know this is theta minus 0 plus 2 this time. So I actually have a vertical shift. So I know here that my absolute value of A is 3, that's the amplitude, my phase shift is 0, my vertical shift is 2, my period is going to be 2 pi over k, which is just 2 pi over 1. So my period over 4 is just 2 pi over 4, which is pi over 2. I'm going to use all this to draw a graph in the r theta plane, going up to 2 pi. The first thing you do is you put in the vertical shift. So the vertical shift here is at 2. So that's like my new baseline. I'm going to move up from this and down from this, right? So the amplitude is 3, which means from the baseline, which is the vertical shift, I'm going to go up 3 units. So that would get me to 5. And that's the maximum height. And I can go down 3 units. So that would get me to like -1. So this is me moving up by A and then down by A from the vertical shift line. Now, everything is going to happen on a grid from 0 to 2 pi. Now, The period over 4 is what I'm going to actually do. So the period is 2 pi. Every 2 pi, I want to slice it into 4. So that's going to give me each one pi over 2. So I'm going to slice this whole thing into 4. And so this is going to be pi over 2, pi, 3 pi over 2, 2 pi. All right, so this is 0, pi over 2, pi, 3 pi over 2, 2 pi. And now I want to graph a negative cosine graph. Now we know how cosine behaves. Normally it starts at the top, then goes down, and then comes back up. But it's negative, it's going to start from the bottom. So it's going to start from the bottom here, then hits the middle, then hits the top, then hits the middle, then hits the bottom. And so this is the graph here. Okay, so that's the cosine graph. That's just me graphing 2 minus 3 cosine theta, like the actual graph of the trig function in the r theta plane. We're actually going to use this to graph the other one. So now I'm going to go down. So remember what I said, all these numbers that you have on the y-axis, those guys are going to be the distances you are away from the origin. You take all their absolute values and you draw circles of those radii. So we're going to have a circle of radius 1, circle of radius 2, circle of radius 5. So we're going to do that. So I'm going to go in the xy. I'm going to have a circle of radius 5. A circle of radius 2. And a circle of radius 1. This is 1, this is 2, this is 5, right? It's just the absolute value of all the guys that show up on the r-axis, right? So those are going to be my distances. Then I'm going to put in the angles. Now the angles, these are 0, which is equivalent to 2 pi. I'm going to put in the pi over 2, which is here. I'm going to put in the pi, which is here. I'm going to put in the 3 pi over 2, which is here. And the 2 pi is already there. So these are happening on the axes. And I'm simply going to follow what this curve above me says. For each angle, I'm going to look at the distance and I'm going to plot it. So notice that when my angle is 0, my r value is at -1. Now the angle 0 is in this direction. I want to be -1, so I want to move in the opposite direction. And I'm on the circle of radius 1. So it all starts right here at the angle of 0. Now, as I move to pi over, now there's another angle we have to worry about. We actually hit 0 here. So these are places where we go to the origin. Now, where are those red points, the intercepts? Need to put those in. This is where 2 minus 3 cosine theta equals 0. So this means cosine theta equals 2/3. So your cosine, so your theta is equal to the cosine inverse of 2/3. So you might not know exactly what that is. That's not a nice number, but we can see here it happens between 0 and pi over 2. So I'm just going to put in a random angle between 0 and pi over 2. That is going to be the cosine inverse of 2/3. There's also an angle here that happens between 3 pi over 2 and 2 pi. So I'm going to put that in. And by reference angles, I know that this angle is going to be 2 pi minus cosine inverse 2/3. So the grid points are important. And if you hit the actual horizontal axis, that's important because that means you're at a distance 0 from the origin. And so you want to know what those points are. So yeah, so we actually hit the first point here. So we would go boom. We know we go to hit the origin first. So that's me going in this arc right here. Now I'm at this angle and I'm moving towards the pi/2. So notice that from here to go towards pi/2, by the time I reach pi/2, I am on the circle of radius 2. So from here, I'm going to jump to the circle of radius 2. Now, from this point, my next stop is at the angle pi, where I'm here, which is on the circle of radius 5. So from moving from pi/2 to pi, I'm going to jump from the circle of radius 2 to the circle of radius 5. Boom. So I end up there. So at pi, I'm a distance 5 units away from the origin. Then my next point to hit is here. So at 3 pi/2, I am back on the circle of radius 2. So from here, I'm going to go back to the circle of radius 2. By the time I'm at 3 pi/2. Now, after this, I'm going to hit this. I'm going to have to go back to the origin at that angle. So I know from here, I don't want to pass this angle. I have to go to the origin before hitting that angle. So it means I have to go here. Now, the last thing, I'm moving from here to here. So this puts me at the angle of 2 pi, and my distance is -1. So that's actually a distance of 1 going in the opposite direction of 2 pi. 2 pi is to the right, which means I'm going to move to the left and close that loop. So the white curve is going to be like this little heart shape with a loop inside. And you'll notice that that looks like this guy. Well, not drawn to scale, but you get the idea. So that kind of shows how to actually use a trig graph to get to a polar graph when you have some sort of transformation of your trig function, where what you were doing before doesn't really help. So technically, if you were to have r equals 2 minus 3 cosine theta, you can multiply by r. So this would be x squared plus y squared equals 2r. So this part here is the tricky part. Like this part is what makes it not a function, because this part here is going to be plus or minus the radical of x squared plus y squared. And then you have the plus, the minus 3x. So this branches off into two things that you're graphing, which is how you can get a loop and it still be a function in the r theta plane. So you're graphing x squared plus y squared equals 2 times the radical of x squared plus y squared minus 3x, and you're graphing x squared plus y squared equals negative 2 minus 3x. So the one with the positive radical gives you the upper part, the one with the negative radical gives you the lower part. And so strictly speaking, this isn't graphing a function in the xy plane. So you don't expect it to pass a vertical line test, but you're graphing this crazy monstrosity, which, come on, if you gave a Calc 1 student to graph this, they would take forever to actually graph it. But if you convert it to polar coordinates, you can actually graph it by hand pretty easily. Well, easily. So, any questions? I don't know. Maybe you guys want to practice some and before you ask questions. I don't know if, I mean, did anything I say was confusing, or do you kind of follow what I was doing? Like maybe I should ask that question. So there are 3 more examples here to try your hand at. So you can try on B, C, and D and E. And you know the answers because they're right here. But of course, don't look at them before you actually graph it. Just try to do the kind of things I was showing you here. And see if you can recreate those graphs. And we'll stop there. The other thing I wanted to show you guys how to do is how to graph ellipses and hyperbolas, but I guess we can move that to tomorrow. That will be the last thing we'll need for the test. So we'll finish up that stuff tomorrow. Didn't quite make it, probably need another half an hour or so. But yeah, this along with, and I guess that's something you could look up on your own. And technically, that's something that you would have done it in pre-calc. Is like how to graph like ellipses and hyperbolas. Is that something you guys did? Probably should have done it. But if you go, I think I put in the notes here. Yes, if you go down, because I was planning on doing that later today. Yeah, you can, I put in the general equations for an ellipse and the general equation for a hyperbola with A's and B's and all that stuff. And I put a list of how to actually sketch them here, but you guys probably remember how to do that from before. But knowing these formulas and being able to sketch them is the last thing you need to know for the test. And I guess we'll cover that probably tomorrow. But it's also something that you could probably do on your own. And you'll just verify everything you did with me tomorrow. Also, practice doing the polar curves. I'll probably graph a couple more tomorrow as well, just to kind of solidify it. That being said, that's where we'll end. So again, test on Thursday, kind of the same format. There's a practice test that's already up that you might want to practice a little bit before taking that. That's technically due on Thursday, but not really. But you can use that to, in addition to doing the homework, what you can do so far, and in addition to the problem sets in the syllabus, the practice test will help you prepare for the test. And so those are both up, and I guess we'll stop right there tonight. So you guys have a good night, and see you guys in the next one.